I'm happy actually to get questions during the talk, okay? Because I'm talking about a different topic than you heard about the last few days, because I'm not talking about scattering SNOM. Zero scattering SNOM in this talk, okay? We do scattering SNOM, but I'm going to talk about photocurrent using the SNOM. And I want to actually first start with introducing what this actually means, photocurrent nanoscopy. And it's actually easier to explain photocurrent nanoscopy than it's to explain photocurrent. Because photocurrent actually means I shine light on a system and a current is generated, right? But then the question is, where is the light shining on the sample? Because it's shining everywhere. So it's actually very complicated, right? Because photons are hitting everywhere and it's generating at these different locations, electric fields and currents and everything, and then there's a total current. So photocurrent is actually difficult to understand in detail. Photocurrent nanoscopy is easier to understand because there's only one place where I shine light, okay? Of course, there's light coming from far field, but for now, just let's assume there's just a local light source, okay? And that comes, of course, from the SNOM tip that is illuminated by light, which can be visible light, infrared light, or terahertz. Now, yes, this thing is a little... What happens is actually four things. First, the incoming radiation generates some excitation. Here I put electron hole pairs because that's the simplest way of how a photon can be absorbed. But as we see later, the incoming radiation with a tip, right, can also generate plasmons, right, or polaritons, or heat, or whatever, right? But it creates something, okay, some excitation in the system. Then this excitation can do potentially nothing, but it can also potentially locally create an electric field. Different mechanisms, I will explain this. It generates some electric field. When that electric field is generated, and you actually see it here in this picture, this electric field starts to drive currents in the system. And some of these currents, and they're shown here in these red lines. And this is actually calculation, so it's a beautiful image, thanks to Mark Lundeberg, but it's actually a calculation of what happens. Some of these currents start actually just circulating, and nobody knows about those. Okay, I cannot measure them. But some of these currents actually make it all the way to the metallic contacts. And when I measure now the current, just with my current meter, from this contact to this contact, I actually will measure this. Okay, so locally something happens at a scale of like 10, 20 nanometers, but these contacts can really be far away, microns or even millimeters far away, and I can still measure this effect. So some of these field lines, these current field lines will always make it into the contacts. So that is actually quite special, so we also call it like non-local probing. And you can actually even use very large devices and probe photocurrents and make then, by moving the tip, make then images of the photocurrent nanoscopy and learn about the system. So I just wanted to go back in time. I did this actually yesterday. No, it was not completely true because we cited these papers, but I was looking at them again because photocurrent nanoscopy is not new. It was already done back in 1996, mostly with visible light, and it was initially used to look at solar cells, okay, to understand how currents and voltages are generated in solar cells, right? Here is work from 96, where they look at spectra. So they use different excitation energies and then try to understand at which location photocurrent was generated. Then there is work from a couple of years later where they looked at spatial profiles and they tried to understand the effect of defects, and they could basically overlay the AFM, which has different corrugations, and at those corrugations, there is also a stronger generation of photoresponse. And then there is work a couple of years later where they looked at nanowires, and they could look at the photoresponse that was always taking place near the contact. So this is SEM image, and this is the photoresponse, and you can see some signal near the contact. Okay, so then we took it basically later on to two-dimensional materials where infrared and terahertz light creates a much more rich spatial profile that led us to learn a lot more about the system, the basic physical properties, but also polaritons. Now, this is actually a recent review paper, thanks to the leadership of Justin Song, that is highlighting nice, thank you. What kind of things you can do with photocurrent? Okay, so this is a very busy image, but basically it's called a multi-physics diagnostic tool of quantum materials. Okay, and this includes photocurrent in general, which means just far-field photocurrent and near-field photocurrent. Right here, the tip is even shown here, and you can learn about different phases in this process that I discussed before. Right, so you can learn about the absorption process and basically perform spectroscopy. You can learn about current generation mechanisms. There are many current generation mechanisms, right? There's the thermoelectric effects, or photovoltaic effects. This image is actually showing topological effects. This color here is showing the Berry curvature of the system, so you can learn about the topological phenomena in quantum geometry, etc., in quantum materials. You can also learn about dynamics in the system if you do this time resolved, relaxation dynamics, dynamics of how carriers move in the system. And then by making spatial maps, you can also learn about spatial profiles in the system through the current collection behavior. Right? So all of the steps in a photocurrent generation mechanism are interesting and relevant. It makes interpretation of your data also sometimes challenging, so you really need to think really what you are probing actually, which of these aspects you're probing. Yeah. Okay, so here I'm just listing a couple of things we can learn from the system, right? And there's a longer list. So we can learn about polaritons. And specifically, we initially started this with terahertz, because for terahertz, scattering SNOM is more challenging because of the detector efficiency. So initially, we used actually photocurrents to measure terahertz polaritons. We can learn about Moiré on twisted two-dimensional materials, because they have spatial profile on how the photocurrent is generated, so we can look inside the Moiré unit cell. And also the correlation effects in the Moiré. You can look at charge distributions in your device. I mentioned already before, you can look in topological properties like the quantum geometry. Currently, we're looking at correlated states in twisted graphene, which we can even see in photocurrent nanoscopy. And perhaps there's also interesting stuff in superconductors. Dimitri is also working on that. I think there it's still the question what is actually happening there. But this list probably goes on while we try different things. In many of these cases, we basically just try it. So we put in a sample, we measure photocurrent nanoscopy, and see if something cool appears, right? And I think Dimitri has the same strategy. And then afterwards, we try to explain. In most of the cases, most of the data I showed, nothing was predicted, okay? Okay, so what I'm going to do now is to focus a little bit on graphene, because it's a bit easier to explain the mechanism, it's well understood. And then I will again mention different systems. So in graphene, you have different photodetection mechanisms. For example, photothermoelectric effect, where basically heat generates a voltage. You can have bolometric effects, where heat changes the conductivity of the system. You have photovoltaic effects where electron and hole pairs are separated, like in semiconductors. And then there is in terahertz also more exotic effects like Dyakonov-Shor I will not discuss. But let's just have a look at these two. I think you're very much familiar with photovoltaic effects. And this is actually very common in semiconductors, right? A photon generates electron and hole. There's an electric field. And this electric field separates the hole from the electron. Okay, and that generates current. This is strong in semiconductors. It's actually very weak in graphene. Why? Because you're not asking questions, so I'm going to ask you questions. Yes, why is this weak in graphene? Yeah. There's no band gap, exactly. There's no band gap, so what happens? So the electron and holes basically just immediately recombine. Yeah. There's no gap. So they don't need to lose energy by emitting a photon or a phonon. So they basically immediately find each other. Okay. So they relax very quickly to the bottom of the band, right? And here as well. When I create an electron somewhere there at high energy, it goes very quickly to the bottom of the band. Same thing with a hole, goes quickly to the bottom of the band. If these two bands are touching each other, like in graphene, the electrons and the hole just find each other, okay? So this is actually the picture of graphene. So if I create electron and hole, they immediately find each other. They can go to the bottom of the band. Now, is everything lost? No. Because what is preserved in graphene, when I shine light, is actually that the electrons do get a bit hotter. So even if the electrons and holes recombine, what happens, so here this is now actually a picture of the Fermi-Dirac distribution, and you can see the Fermi energy in graphene is not very sharply defined anymore, it's actually smeared out a bit. And the more light I shine on the system, the hotter it gets, okay? But it's not the phonons, it's actually the electrons that are hot. Yeah? And this is a very simple picture, just to understand that this Fermi-Dirac distribution is smeared out a bit. Now, this electronic heat can generate a voltage through the photothermoelectric effect, which is basically also called a Seebeck effect. And that happens when I have a difference in Seebeck coefficient. And let me explain that. So let's go back to the thermoelectric effect, which I think you all know very well. You have two different materials that have a different thermoelectric coefficient, also called Seebeck coefficient. And then if there's a temperature difference between the two, then a voltage is generated. Okay, and that's very simple, shown in this equation, right? A delta T and a delta S leads to a voltage. So in this case, two different materials. That's just the standard classical thermoelectric effect that you learn about at high school. Now, in two-dimensional materials, I don't need two different materials. I can do it with the same material. The only thing is, I can, to make a different Seebeck, I just have a different doping. I use different doping. Okay, so I have graphene, for example. In region 1, I have p-type doping. Okay, the Fermi energy here is below the Dirac point. And then on the right side, I have n-type doping. It gives me a p-n junction. But I don't even need a p-n junction. I just need different doping. Okay, that I can do with a gate. So graphene you can gate. So this is a simple picture of that geometry. So this is graphene with contacts. On the bottom, this is doped silicon. I apply a voltage between the two, and that changes the doping in the graphene, right? So basically, if I do that, I can plot now the Fermi energy as a function of voltage. On the left side, I get hole doping. Then there is no doping in the middle, and on the right side, there's electron doping. That's a typical gating of graphene, but now I can do this in two different regions, okay? So I can do this with two different gates, or initially work that we did back in 2011 is actually just to have a narrow top gate in combination with a back gate, okay? And then you can get two different regions. So on the top gate, the doping is different from, to the left of the top gate or to the right of the top gate, and then that gives a difference in Seebeck coefficient, and that can lead to a photothermoelectric effect. So this is not photocurrent nanoscopy, right? This is just photocurrent, where you basically focus the beam as good as you can, and then scan it over the device, and then you obtain this kind of photocurrent image. So this is basically the current generated in the system as a function of laser spot position. And you can see these spots here, and those are actually taking place exactly where the Seebeck coefficient has the strongest gradient, right? So there's Seebeck is large here and smaller here, and so there's a large difference in Seebeck exactly at this junction. Okay? Let me ask any questions, because if this is not clear, then the rest of the lecture is just useless. You can just go for coffee, okay? So, yeah. Okay, Adrian has a question. Yeah.
How large? I don't see any scale bar.
Ah, sorry, yeah. Of course, nanoscopy people want to always scale bars. This is done with a visible light laser. This is a 10 micron or something like that. So everything is big here, right? There is no nanoscopy, this focused light, and then these spots are also quite big, right?
How long does it take to record such an image, let's say?
Oh, that's quite quick, a few minutes. Yeah. Okay, so this can be understood in a simple picture, right? So I have graphene with slightly different doping, okay? And therefore, the Seebeck is different. And then if I shine light on the system, I create some hot electrons. I just draw them here now as excited electrons. And then a current starts to flow from here to here, okay? And that is called the photothermoelectric effect. This is the equation. So the current is basically the integral of the electric field that's generated, and then the electric field that is generated is basically the Seebeck coefficient times the gradient of the temperature. I will go in more detail because in reality it's a bit more complicated, okay? So this Seebeck coefficient in graphene has a specific form, and you can calculate it with what is called a Mott equation. This is actually a generic equation that you can apply to any material. It has some prefactors. Then it has G is the conductivity of the system. And what you need is basically the conductivity derivative over the Fermi energy in the system. But I can also just write it here as a derivative of the conductivity of the gate voltage, right? Which changes the Fermi energy. Why I do that? Because then I can actually look at a simple conductivity measurement. So reminder again, right? If I measure the conductivity in graphene as a function of gate voltage, I have low conductivity when the Fermi energy is at the Dirac point, right? And then on the left side here, I have hole doping, so the conductivity goes up. On the right side, I have electron doping, conductivity goes up. So this is the conductivity of graphene. I take the derivative, and then I get something like this, right? And that's the Seebeck coefficient. This is the predicted Seebeck coefficient, but you can also then calculate it, and it almost always agrees perfectly. So it's a little bit, for graphene, the Seebeck is a little bit wild, right? It goes up, then it goes down again, changes sign, and then up again. So it's non-monotonic. It leads to some interesting behavior. But for the nanoscopy, you don't even care too much about this, okay? The only thing, that you see clearly at the Dirac point, it changes sign. And we'll see this in our images. So this is work from MIT, where they measured the photoresponse now with 2 gates, basically to go through all the configurations, right? Means left side p-type doped, right side n-type doped, or NP or PP and NN, right? So then you can make a whole matrix of all the different configurations. And what you see here is that the sign of the photocurrent is changing several times. So it's positive here, back to positive, negative again, positive, negative. And the reason is exactly because of this funky shape of the Seebeck coefficient, right? Now, I'm showing this because this was actually proof that the photothermoelectric effect is dominant here, because you can actually look at the system. There's an electric field pointing to the right, and the photovoltaic current would, if there was a photovoltaic effect, right, it would always go in the same direction, right? But actually, there are regimes here where the current is in the opposite direction. Opposite direction as the electric field, so that's proof it's photothermoelectric. And I will come back actually to this equation later. Then you may wonder also about the size here of this response. And that's another important parameter in the system, also for nanoscopy. This is not the laser spot size. This is actually the electronic cooling length. This is actually the distance that hot electrons can diffuse before they cool down. Right? So let's say I have a local spot now. It heats up electrons. These electrons start cooling, but they also move. So you can imagine that the thermal profile is basically decaying as a function of space, right? And that typical length scale is the cooling length.
Frank, how about the substrate? Do you take into account any substrate effects?
Yes, actually, the cooling length is in many cases dominated by the substrate. So the heat is actually lost into substrate phonons, for example. Because there's also coupling to graphene phonons. This is actually very weak. And we have a paper, which is not in the slides, which shows actually that the cooling to the hyperbolic phonons in boron nitride is very strong. So actually, the hyperbolic character that Pablo was talking about is actually important for the electron cooling. Why is this important? Because the cooling length here actually, in the end, enters also the equation that I obtained to calculate the spatial profiles of the photocurrent. But I will come back to that. Okay. So I will skip this. I will just mention quickly that in graphene, the photothermoelectric effect is strong, not only because the Seebeck is large, but also because the coupling between electrons and phonons is very weak. So that means that the electrons get actually relatively hot. And that's the reason, I think, why this photocurrent nanoscopy works so well. So initially, we started doing that in 2016. We did this on CVD graphene. It's Achim Wusner. Some of you know him. And I told him, let's look for plasmons with photocurrent, and with no clue that this could actually work. And then he tried for quite some time and didn't see any plasmons. And then we're like, oh, we don't even know why we would see them, so let's forget about it. But actually, then later on, he did see it. But the mistake was to actually look at CVD graphene, which has a lower mobility. I think it's even lower here, 1,000. But when you do photocurrent nanoscopy on CVD graphene, you see this, okay? So it looks like a mass, right? The edges are here. It's like a cross. The contacts are here. And it looks like a mass. That's not because the technique is a mass. It's actually because the material is a mass, okay? So CVD graphene is actually low quality. And if you zoom in, you can see here now all these sign changes, right? And I mentioned already, the Seebeck coefficient changes sign at the Dirac point. So these are doping variations, positive and negative. And if you look here, you zoom in, you can actually see here grain boundaries in the system, where the system changes also doping. And these are the grains that happens when you grow CVD graphene. We can also measure this as a function of voltage. We can indeed even flip this sign change by changing the voltage. and prove that this is indeed a change in carrier polarity. Okay, so why is this useful? Okay, we can see grain boundaries, we can measure the carrier distribution, we can see that it's a messy system. Then we go to higher quality graphene. This is exfoliated graphene, but without boron nitride. If we are now close to charge neutrality, you can see all the puddles here. Electrons and holes. They're randomly distributed, but only at charge neutrality. Okay, this is now a line cut as a function of gate voltage, and exactly charge neutrality, you can see all the puddles, but away from it, it's nicely and uniform, right? And at charge neutrality, there will actually always be puddles. It's just in higher quality graphene, this is a smaller region, a smaller gate region where this happens. Okay, so we can learn about puddles. Then we look at encapsulated graphene. We could actually see that there is no puddles anymore, but then we saw that near the edges, there are very sharp, there's a very sharp photoresponse, and this has to do with the, doping that builds up near the edge. That can happen even in HBN encapsulated graphene, and this comes from actually the silicon oxide substrate. So that's why people now actually use metallic local gates to get rid of this oxide effect. Yeah.
I see the currents are really large compared to the CVD. It's like 100 times higher. Is this for the same voltage that you apply?
Yeah, they're much larger. It is because this is a very well-defined junction. I will show later, but basically we're probing the gradient of the Seebeck coefficient. And if there's a very sharp jump in Seebeck, you get a larger photocurrent.
How does it compare to a far field measurement? I don't remember the values. It was also nanoamperes, but was much higher.
Far field.
When you showed the very first large area with the focus.
Similar numbers, but complete coincidence, right? Because here we basically use still the tapping of the tip, and then we use a lock-in to measure the photocurrent, right? At tapping frequency, so it's completely different from the far field. Yeah. And the power at the tip is much lower. But we were surprised that actually the signals are so large, right? Because your local laser spot, your local hotspot is much smaller, right?
Exactly.
Than your laser spot.
This is surprising, you have to see.
Yeah.
Values are comparable.
Yes. But of course, the field is enhanced, right? So, okay. Now, a little bit about like why does this actually work, right? So I already mentioned that that there's multiple steps in the photocurrent generation mechanism, and the mechanism that you basically locally perturb the system and then globally can probe it is something that goes all the way back from the old days of Shockley, who you probably know very well by name, and Shockley and Rameau already predicted non-local photocurrents, which basically aligns with this picture that I mentioned before, right? Is that you locally perturb the systems and that some of the current lines make it all the way to the contacts. Okay, so I explained this already before. I just wanted to mention here it's called Shockley-Rameau. And you can actually find, the reference is gone, but this was initially in a paper by Levitov and Justin Song. Now, here I wanted to mention briefly how to now calculate these spatial images of the photocurrent. And so the naive way would basically say, let me just take a local source, a local heat source. Then I calculate the electric field that is generated by this local heat source. Then I calculate current profiles, and then I integrate over those, and I get a current. And then I have to do this for each spot. So that's a really long calculation. That takes longer than taking the experimental data. Okay? It turns out you can actually use reciprocity in the system. There's Mark Lundeberg actually nicely worked this out. There's a paper is on the archive. and it will be on the archive forever because Mark went into cryptocurrency, and you know, he's not submitting this paper anymore, so we just leave it on the archive, but it's very useful. So what you do is that you basically calculate first equipotential lines. So you basically say, oh, let's apply a bias between source and drain, and then look at the voltage distribution, or you can actually see these lines of how currents would flow. So now I am, you know, simulating this system, which I showed you the data before. I just flipped it upside down and showed this data, where there's a bit of doping near the edge. So the current is actually going to flow a bit more near the edge than in the bulk, okay? And so these are the equipotential lines. And then by taking the gradient of this equipotential line, you can immediately obtain the photocurrent map, okay, in one shot. So I don't need to do this tedious process. That's explained in this paper. Here are the equations. So here you can see the gradient, right, of the voltage of the equipotential lines. So this is a very powerful way to calculate photocurrent maps. Yes?
A quick question. I mean, now you described the forward way, right? But how would it be the opposite way if you would take the photocurrent method and try to reconstruct all these, all the equipotential lines? I mean, would there be a unique solution, or would you end up with eventually different?
We do it iteratively. There are probably more solutions, but some of them are not really physical. So we play basically with some seabed profile, and then iteratively we try to find it, which is a lot more complicated process. So it's hard to do the inverse of this. So you can do this, but let me give you a simple equation, and I think I showed you this one before, which is more or less an approximation of the system. So the current that is flowing is basically a spatial integral, and I'll make it one-dimensional, okay? It's a spatial integral of the gradient of the Seebeck coefficient times this exponential decay of the cooling length, okay? And then you spatially integrate this. So what you have to remember is what we're probing is basically gradients of the Seebeck. And that's how we can do the inverse sometimes, because then we just take the integral and then we have a good approximation of the Seebeck profile. Okay, so this was all back then. We looked into encapsulated graphene. We didn't see plasmons in the photocurrent. Then we almost gave up. Why did we believe that it was actually good to look at plasmons with photocurrent? Because a graphene plasmon decays into hot carriers for 80%, at least at room temperature. I think at low temperature it's more phonons, as Dimitri Basov showed, but a lot of the decay product of the plasmon is heat. So why don't we use it, right? Maybe also for energy harvesting, but also for detection. Then we thought, okay, let's make a very well-defined sharp junction, launch plasmons, and if these plasmons decay, they will at some point hit this junction and then generate a photoresponse. Or the plasmon decays into heat, and heat diffuses to the junction and generates a photoresponse, right? So, so this was the experiment. So this was now a well-defined junction with a split gate, where the gap between the gates is very small. So there's a very strong jump in the Seebeck coefficient. So the gradient of the Seebeck is very large. We do now photocurrent mapping. Now there is, okay, this is a scale, this is microns, but you see a very thin line here, and this is the photoresponse at the PN junction, now with photocurrent nanoscopy, and it looks like a line, okay, as expected. But so still no plasmons, right? But if you zoom in at the edge, so here's again the line, we zoom in near the edge, and near the edge we saw oscillations, okay? And then we were initially surprised, actually, because the oscillations are actually very clear, and we were worried that this would be smeared out completely by this electronic cooling length and the diffusion and all of that, right? But you can see very clearly the oscillations. And actually the signal to noise in some cases even better than scattering SNOM.
Frank, short question.
Yeah.
Does indirect illumination plays a role in these measurements? So it's of course the nano focus from the tip, but
yeah. Okay, so yeah, I should have mentioned this more clearly. So the way this measurement is done is that we lock into the tip modulation frequency. So we don't see the background there. Well, sometimes there is, of course, some background from the tip reflection, etc. But it's relatively weak. You can see that. You can see that by here that the background here is nearly zero. Okay, here you can see the experimental data, and you can see in the many fringes here, they more than 10. Okay, so how can we model this now? And why is this happening near the edge? So you can basically see this now as the plasmon as the heat source, okay? But the heat source is coming from the plasmon interference, right? Because the plasmon launched by the tip, reflected, Pablo explained it. When they coherently interfere, then there is more heat produced than when they destructively interfere. You can understand this basically from wavefronts of the plasmon, and then from that you can calculate the decay heat, and in that way you can perfectly model the heat generation from this plasmon that oscillates near the edge. And all of the details are in this paper, also from Mark Lundeberg. So that you can calculate it very well. Was not predicted, but we were very excited we can see plasmons in this way. For infrared, this is nice, but you can use scattering for terahertz. This turned out to be very useful. And this was, I'm sorry, there's some old slides here, so sometimes it says in print, but 2016. I was collecting some, old slides yesterday. This is work with Pablo. The measurements are also done in Nanogune because they had the gas laser. Later on, we also bought the gas laser. Now we have 3 gas lasers, actually. And for terahertz, this works beautifully. Okay, so here you can see same PN junction, same device, actually. You see these oscillations near the edge. This is a 3D image of the data, and it's quite amazing. Right? The signal to noise is amazing. This is now the gas laser in our lab. My kids, he's now 11 years old, okay? So this is already quite a couple of years ago. But think of it, right? This is the huge gas laser, 3 meters long, coupled into the NEA SNOM. And then locally, a spot of 20 nanometers generating this heat source, right? And then you can see terahertz plasmons. I find it fantastic, right? That this is all possible. We did not predict that this would work. I think for the students, it's like, I always tell them, when you believe that something does not work or your supervisor says will not work, you should try it because it's a good chance it will work. If your supervisor says this will for sure work, usually it doesn't. Okay, okay, so here you can see, you can measure now for different frequencies. One thing that we found here with terahertz plasmons is that, first of all, the dispersion is linear. Pablo just explained to you plasmons graphene are square root of k. It's linear. This is because there is actually a gate close by, and the wavelength of the plasmon is much larger. And then you get basically screening of the plasmon by the metal. And you can see this as an image, as a mirror image. So you can actually see it as 2 layers of graphene, where the excitation has exactly the opposite polarity. And this is called a screened plasmon, and this leads to a linear plasmon dispersion, also called acoustic plasmon. So this acoustic plasmon, as you can see, has also a velocity that's much smaller than the typical graphene plasmon. And then what we saw is that we could slow it down to a very small velocity. A velocity that is close to the electron Fermi velocity. And then we came up with this picture here, which is, this image here is basically showing the electron surfing the wave. Okay? So when you go surfing, you pedal, right, really fast. And why you do that, right? Because you want to obtain the same velocity as the wave, and then the wave catches you, right? If you don't know this, go surfing, because this is a good place. You have to be there, okay? And it's really the same thing with electrons, okay? So if you have electrons in a plasmonic system, and they have similar velocity, they start to move together. And this has important implications. So this is something we could see using the photocurrent nanoscopy. I won't have time to go in too much detail, but why is this important? Because in that regime, the non-local conductivity of the material system becomes important. And what does that mean? So typically when we think of conductivity, it's called sigma here, or even permittivity, we think of it, that something that just spatially varies, right? And if you take now the Fourier transform, it just has a spectrum as a function of omega. Now, it turns out that the non-local conductivity, let's just look in Fourier space, has a momentum dependence. And usually we ignore that. Same thing with permittivity. So usually we ignore the momentum dependence of the permittivity. But it turns out that this is actually quite strong for these terahertz plasmons. This is relevant because it actually measures the direct dynamical screening function of the system, and in solid state physics, there are lots of theory papers on this topic, because you can learn really about the quantum theory of the electron liquid, which is the title of this book written by Giovanni Vignale. Now, so without giving you the full equations, I'm just giving you the picture. This is what it looks like. So if you have a usual plasmon, it is like this, right? So you have a wave, and that consists of some shaking of electrons, okay? And the electrons are just shaking a little bit. But now, if we go to the terahertz, and we slow down the plasmon, so now the plasmon is very slow, you can see, just look at one of the electrons, okay? Put your eye on this one. You can see when this electron is moving forward, it's moving at the same velocity as the plasmon. And then it moves back again, of course, it oscillates. But this is the picture, okay? And then these non-local effects kick in. And the condition is basically that the velocity of the electron, Fermi velocity, divided by frequency is equal to the plasmon wavelength. Okay, so you can already see that you need very small frequency omega for that in order to reach that regime. Okay, now, this is something we could see in the data. So that we measure the terahertz plasmon velocity as a function of doping. You slow it down all the way to the Fermi velocity. You see, this is very nicely how we can measure the velocity of the plasmon. And then here it hits the electron velocity. And then you can see that the classical theory is the dashed line, and the red curve here is the quantum theory, which fits really well with the data. And so from this, you can learn about the system. I will skip this. It's work with Marco Plini. You can learn about the compressibility of the system and Fermi velocity renormalization effect, etc. And we're actually applying this now at low temperature to see more correlated effects. I think Dimitri's looking also at hydrodynamic effects. So this will follow up. Okay, now I want to move on. Some other things you can do with photocurrent nanoscopy. So you can look also at phonon polaritons. So this is just graphene encapsulated in HBN. It turned out that if you have the split gate and you launch phonon polaritons, as Pablo showed, they behave like these rays. They are absorbed in the graphene, and they can also generate a photocurrent. And then you see fringes here, which is coming from the phonon polaritons. Dimitri published this work recently where they had even enhancement of photocurrent patterns using from the hyperbolic phonon polaritons. And this is Moiré systems, which I will show you in more detail in a second, so I won't go into too much detail here. But they saw this splitting here, which is related to the phonon polaritons. Now, to go to Moiré systems and graphene and twisted graphene, you need to go to low temperature. So we bought a cryo SNOM. This was actually around COVID time. This was just before COVID, okay? So Khaled Karai even came to our lab to help installing it, together, of course, with the other people from NeaSpec. We were very happy. Then COVID hit, so the lab shut down. Then NeaSpec people couldn't fly to Barcelona, and so we had some challenges to get it to work. But thanks to Niels Hesp, we got it to work, but we're using it mostly for photocurrent right now because it's producing a lot of interesting data and easier to operate. Look in the thesis of Niels Hesp, because there are some tricks actually that are useful for the cryo SNOM. One of them is actually active damping. So our system is not in a basement, so we do suffer from building vibrations. And Niels came up with this active damping, which is basically big pieces of metal, very heavy. And on the bottom there's a piezo, and then we have an accelerometer sitting on the ground somewhere, and then with active feedback is actually compensating the vibrations. Exactly, it's 16 hertz, which is the eigenfrequency of this cryo SNOM. So that helped a lot. And so eventually Niels got this to work, and we're producing interesting data, a couple of papers in a review related to twisted two-dimensional materials. Now, twisted materials, Adrian, do I still have time? Because, oh yeah, okay. Okay, twisted materials create Moiré pattern, right? A periodic pattern. You can see it in this PowerPoint image. You see this periodic modulation. And electrons feel this periodic modulation, and that changes the band structure of the system. And in the case of HBN and MOF3, it changes the polaritonic properties. But here I'm talking about the electronic properties, right? Now, this became a big thing because of superconductivity and magnetism that were discovered. So initially, we were just looking at this system with a SNOM and cryo SNOM, different angles. And so one thing that is relevant here is when you change the angle of the system, lattice relaxation takes place. What does that mean? That means that actually this beautiful periodic structure that you see in PowerPoint is not a reality. The reality is that because of the system wants to minimize energy, it's going to actually minimize these regions here and maximize, sorry, it's going to minimize AA region, which are energetically less favorable. You can see that here in this picture when you calculate the Moiré pattern for different twist angle. Initially it's periodic here, and now you go to smaller twist angle, and you start to see more of this lattice relaxation, which then leads to triangular patterns. Okay, and you can see now the AA region is smaller and the AB region is larger. Right? So AA basically means the atoms are on top of each other, and AB means the atoms are not on top of each other. You can imagine that energetically, the system wants to be more an AB, right? So for small angle, this happens. For larger angle, this doesn't happen because it periodically varying so rapidly that it will cost the system too much energy to reconstruct. So you get these triangles. Now, if you look with photocurrent nanoscopy, this was published not too long ago. Also, Dmitry Basov, similar data. You do now this scanning near field map. It doesn't go that fast. So in practice, it takes a little bit longer. Now you can see in the photocurrent these triangular patterns. And you see also periodic structures changing, right? Here you have very large moire unit cell, here it's smaller. And that means that basically spatially the twist angle is changing. And you see also sign changes, blue and red. We can understand all of that by calculating the photocurrent maps with a method that I mentioned before. Let me actually skip this for now, because I explained that already. But this is something is important. I showed you already that the current field lines, right, are important. And they are different when I use different contacts. So between contact 1 and 3, current field lines look like this. Okay? And between contact 2 and 1, they look like this. And if I have now a Seebeck coefficient, that is shown here in yellow, then it's actually the projection of this current field line on this Seebeck profile that matters. Okay? Because I'm probing again the gradient of the Seebeck. Yeah? So that's why when I measure with 2 different contacts, I get a different spatial profile. And this is now a calculation, and this is the experiment here. Okay, sorry. Now the calculation on the left, on the right side's the experiment. So we can really understand very well this system, right? And then really learn about spatial variations of the Seebeck profile. Okay, that was nice, but the excitement in twisted graphene is magic angle. Okay, what does magic angle mean? That is the twist angle of 1.1 degree, and that's where the system becomes magnetic and superconducting, and other correlated phases have been discovered, like Chern insulators. And that's basically where the velocity of the electrons is not anymore a Dirac cone, like shown here, but it's actually a flat band, which means the electrons are basically in a standstill, they're quasi-localized. Okay, so that was the discovery in 2018 by the MIT group. They saw many emergent phases later on by different groups. Also, Wigner crystallization has been observed in twisted two-dimensional superconductors, semiconductors. Spin triplet superconductivity has been seen in tri-layer graphene systems, ferromagnetism, etc. Okay, but the system has one challenge, which is that there are spatial variations of twist angle and strain. So nanoscopy is important, and I think this is perfect for our system. Also, infrared and terahertz is ideal because infrared light excites in this magic angle graphene between the ground state and the remote band here, 100 millieV, and terahertz actually excites between the flat bands. And I can't show you the data, but we have very exciting results here for the terahertz, where we can see the full evolution of the correlated states that are happening in these flat bands in photocurrent, also in near field. But the most basic thing to initially look at is just, again, the Seebeck, right? And the Seebeck in twisted magic angle graphene is a bit more interesting, because in addition to the usual sign change that I showed you before, there's another peak here. And the horizontal axis is actually filling. This means filling 1. And filling 1 actually means that in my moire, I have 1 electron in each moire. In practice, it's 4 because of valley and spin degeneracy, but forget about this. So let's just say about 1 electron. So you can see this moire is an egg basket, right? And when I put 1 electron in each of those baskets, then I have full filling, and the system becomes insulating. Actually, I fill this band, then there's a gap here, and that's why the peak in the Seebeck emerges. Can we see that in nanoscopy? Yes, we can. We take now spatial images. The scale bar here is micron, but here you can see also the scale in microns. This is now measured at different voltages. It looks like a mess. Why? Because there's variations of twist angle. But if you now take a line trace here, and I plot it here, and the other axis is the voltage, I can actually see what I showed you before. This peak in the seeback here and here, okay? And that's the full filling. So that we can understand. So now we take some different line cuts here. You can see indeed this peak here. So at each location, I can now measure the voltage for which the seeback peaks, and then from that, I can actually extract the twist angle. Because from this density, I can actually get a length scale, and the length scale tells me the size of the Moiré unit cell, and the size tells me what is the twist angle. So then from this, I can then now make a spatial map obtained then from photocurrent nanoscopy, so 20 nanometer resolution, of the twist angle of the system. Okay? This map looks kind of random, but we have now higher quality samples where we start to see larger domains that have triangular structures, etc. And so the cool thing is now that we can understand much better when we see correlations, and unfortunately I cannot show them now, but I can show you after the talk in private. We can see correlations or even value polarization in certain areas and not in other areas, and so we can relate now the twist angle variations to the correlations in the system. This is actually the data set with artistic blurring, so that we can still put it on YouTube. So we can see it integer fillings, the correlations. So this is ongoing experiments. Another very exciting direction, so I'm finishing now, another very exciting direction, I think, and Dimitri did some initial work on that, is the fact that you can have other photocurrent mechanisms that are related to the topology of the system. And I think many of you are familiar with Berry curvature, okay, which is an intrinsic material property. Then there's other topological phenomena that are related to Berry curvature dipole, okay? But there's also a quantum metric, which is also an interesting, an intrinsic, let's call it topological property that is less well known, but all of these different topological properties can generate photocurrents. And the only requirement is that your material breaks inversion symmetry. Sorry, it's not the only requirement, it's a minimum requirement. So in many quantum materials, this is the case. It's actually also the case in twisted graphene. It's a chiral system, so inversion symmetry is broken. But also in wild semi-metals, and you can see here many of the topological materials are mentioned here. And then for different symmetry breakings, there are different mechanisms. So here it shows the inversion symmetry breaking, which is the case in all of these. But then if you break time reversal symmetry, like in these two, you also get different photocurrent mechanisms. So in that way, you can even use it as a probe to measure the symmetry breaking in the system, and then hopefully with nanoscale spatial resolution. And we have some initial data on that as well, but there's also a paper from Dimitri from, I don't know, what, last year or something like that, right? Where they saw also nonlinear photocurrents in wild semi-metal that is explained by these by this picture that I showed you here. And now I want to finish. Thank you very much.
Thank you, Frank. Questions? Yes?
Okay.
Thank you for the talk. You mentioned using the technique on nanowires, and I'm intrigued to see how challenging it is to use it for a single nanowire as a photodetector. And is that sensitive to the antenna geometry? I mean, the contact,
Right.
whether it was a straight line or a bow tie kind of thing, then bridging the gap. And given the spot size, and now, is that also sensitive to your nanowire shape, if it's cylindrical shape kind of stuff? And follow up to that question also, what prior knowledge I should have for a nanowire? Because many factors come into the play, fabrications, given that. Is there any analysis that or characterization I should do before resorting to kind of mapping out the photocurrent?
Which material nanowires are you working with?
It's cadmium arsenide,
Okay, so...
which is not a quite semiconductor, but it could behave as a...
Yes. So it's not difficult because I assume you deposit on the substrate, right?
Yeah.
So, of course, contacting wires is always challenging, but it's a separate story, so I'm not going to talk about that. But imaging them with nanoscopy is very easy. So I've actually also done it on germanium nanowires before this work. If you use far field, you will have antenna effects. Okay, so near the contacts, if you have the polarization perpendicular to the contact, you get an enhancement of the signal. But if you use nanoscopy, you don't have that because your antenna is really the tip, right? So then you just have to make sure you don't scan over the contact. But if you stay on the wire, you can very nicely measure the potential profile in the nanowire, especially if you have a gate.
Right. Oh, thank you.
Yeah.
My question is, did you try a nanoscopy of multi-layer graphene with different stacking orders to resolve the boundaries, like ABC, ABCD?
Yes, we did, but Dimitri actually published papers on that topic, so they do see, this was, I think, tri-layer graphene, right? They did tri-layer graphene, there are different stacking orders, right? ABC and ABA, and that gives a different, I think also give a different scattering signal. So you can even see it in scattering in that case. But in photocurrent, I'm sure you will also see it because the Seebeck coefficient is different. Yeah.
Thank you. Very nice talk. Just a question about the probing volume. Is it different in the case of with respect to SNOM? For example, can you probe more volume? I'm asking because, like, for example, in these twisted materials, sometimes you can have like a top layer which is thicker, so your moire pattern is literally buried. So is it something that can you comment on?
So when we encapsulate graphene with HBN and we want to see plasmons in scattering, we have to make the top HBN thinner than 10 nanometers, okay, in scattering. If you use photocurrent, we can live with a little bit thicker HBN. So it's not fully understood why, but I think the simplest picture here is like, in both cases, you still have just the volume of your hotspot, right? But with scattering, you have a double process, so very inefficient, right? And with photocurrent, it's only one process, in, and then it goes in the graphene, right? So you have a little bit, you can bury it a little bit more.
Okay, just further comment. Are you demodulating the signal somehow? Like
yeah, just with the tip frequency.
The tip frequency, okay.
Yeah.
So like the signal that you showed are like demodulated that they are higher harmonics of the tips?
No, it's just the harmonic of the tip.
Okay,
yeah.
Okay. Thank you.
Thank you, Frank, for the nice talk. I was wondering about temperatures. So for addressing or to see all these phenomena on twist graphene layers, what temperature should we operate? I mean, can we see this at room temperature, or it needs to be very low temperature?
Yeah, so for example, this, you definitely need low temperature. As I mentioned to you yesterday at dinner, look at these flat bands, right? They are as flat as like 10 millieV. And KT, room temperature, is 30 millieV. So at room temperature, these bands are filled. Well, strictly speaking, half filled because it's a thermal distribution, but the gate does very little. Okay, so you don't see any more. For example, these full filling peaks, right? It's completely smeared out, right? So any paper that claims at room temperature to see effects of quarter filling and three-quarter filling in twisted graphene, that is complete nonsense, okay? And there was a paper in Nature that was actually claiming that. So That's just not possible at room temperature. And that's really basic physics, right? So the flat bands are that flat. So yeah, that's apart from correlated states, right? That's just filling the bands, right? Of course, for correlated states, you usually need lower temperature. However, in bilayer graphene aligned on HBN, also room temperature effects have been seen now that are due to the Moiré pattern. But, okay, but that's a different system. Yeah.
Frank, are there any practical aspects that you could share? Let's say somebody wants to do these measurements. Could you give some advices to avoid any mistakes in doing such?
Yeah. So typically we have what you should do for sure is go to the thesis of Niels Hasp. So it's all written there. So we typically use a nice circuit board to make sure that we have low noise collection of the currents, right? So we have coax lines connected to a circuit board with a chip carrier, and that's just in the NEA spec system, right? That's one thing. But then those coax lines just go to a current amplifier, nothing special. And then the lock-in measurement you can do with your own lock-in, but you can also do with a lock-in that's already in the NEA spec system. So you just feed the amplified current, the current amplifier, the output just goes into the NEA spec electronic system, whereas the lock-in, and that already modulates at the tip frequency. So that's relatively easy. So I would pay most attention to the electronic wiring and a stable circuit board that you can mount on the system. And the design of that is in the thesis of Niels Hasp. So
thank you for sharing this.
Yes, yeah.
Okay, one more question from Vladimir, and then we go to coffee.
Just a very short one. Nanoscopy, it looks similar to usual near-field scattering, but there is no phase. Is there any way to get this phase information, or like additional measurements?
So we do get photocurrent in phase because it's tip modulated. So we do get, amplitude and phase information. And actually, we're using it. We are using it. We are using it to because the system has a capacitive component as well, so you get a complex photo response. Okay, so because resistive part and the capacitive part, and we're using it now to actually understand more about the system. But it's very different from the phase that you're used to with optics, right? So with polariton. So for example, for the polariton imaging, there is not a polariton phase that we obtain. Yeah. But there is another type of phase that tells you more about the material system. So, yeah, depends on what you want. The best is actually combined scattering and photocurrent. Huh? So those images are produced at the same time, huh? The photocurrent and scattering. Huh? So you always have both. So in our lab, we always measure both. So there's no reason to, well, unless you don't have contacts, right? But if you have contacts, why not just probing it, right? Maybe you'll see something in one and not in the other. Huh?
Let's thank Frank again.
Okay.
And